It is a pleasure for me to introduce Zhen Liu. I think I know Zhen since he was a student. He was a PhD student at Fermi Lab some time ago. He graduated from the University of Pittsburgh in the year 2015. And since then, he came to Fermi Lab, worked at the theoretical physics department there between 2015 and 2018. And then from 2018 to 2020, he was at University of Maryland, the Center for Fundamental Physics there. And then now he's an assistant professor position, professor at the University of Minnesota. And Zhen has worked in a broad range of subjects in phenomenology of particle physics, including physics at collider facilities, LHC and future facilities. He has worked on neutrino physics, neutrino also at long baseline neutrino experiments like DUNE and other facilities. And I think that nobody better than him to tell us about the opportunities in energy physics. With that, I pass it. Michael.
First of all, I would like to thank the Aspen Center for Physics for giving me this opportunity to give this talk. My talk today will be about opportunities that strikes high energy physics. I will share with you, from my viewpoint, of the advancements and the prospects in high energy physics. I think it's clear to many people that we have experienced a triumphant endeavor of particle physics in the past century. We established this so-called standard model of particle physics in the quantum field theory with the following particle content, labeled the years when those particles were officially discovered. Okay? You can see the discovery journey starts in the 1800s, but really accelerated in the past half a century or past century. And the standard model of particle physics content is give us the most successful description of the microscopic physics of nature. Also can be connected to a standard model, standard cosmology to give us very consistent descriptions of our universe. Beyond this complex content of all those matter content of quarks and leptons and neutrinos, and also gauge force carriers, and also the Higgs field, the most recently discovered particle, behind the complexity is a beautiful simplification. Okay? We can see that every day we're interacting with electromagnetism, but also we are sure that there's nuclear weak interaction. Those forces are unified together into the electric theory that's really fully established through the discovery of the Higgs boson. And also, we have the strong dynamic quantum dynamics, and theorists have been postulating more unified theories such as supersymmetry or grand unification. When we have been dreaming about unifying with quantum gravity, but those echelons are just postulations. We are trying to find evidence for such possibility. Being so successful in the past gave us a very challenging task for the future. The current status of the field, I believe, is we are standing on the shoulder of our past success, and we are looking into the future. Okay, we are now into a new task, that is to explore the unknown. That makes our field a very vibrant and dynamical field. That's why I say there's a lot of opportunity to striking our field. In our task to explore the unknown, we ultimately and automatically adapted a multi-pronged approach. Okay? The approach can be symbolically represented like the following. We are theorists behind all the possibilities, working closely with our experimental colleagues to explore nature by looking into space, into high energy, high intensity, and also tabletops and information, etc. I will not have time to go through every of them. In fact, several different topics will be covered in other Aspen colloquiums. In the first part of my talk, I would like really to focus on into the high energy physics, because that has been proven to be the very fruitful exploration that enabled us to have many of those fundamental physics discoveries. Into high energy. This is the image of the currently running Large Hadron Collider detector, which there are two main detectors, Atlas and CMS, each 3 to 6 floors tall, is underground. What do we do there? Okay? We try to accelerate particles and in the accelerators and try to smash them together. Those gigantic detectors are trying to detect the events when I smash two ultra high energy protons. In details, that is two very energetic protons hitting each other, producing all different kinds of particles. And we are trying to take the best image of those and reconstruct the underlying events. And we are able to detect various kinds of standard model particles, but what we are interested in is what's the microscopic physics happens in the, at the point of the interaction. And we were able to reconstruct the Higgs boson through the very complex events. Okay. So, having such a introduction, I would like to go back to history a little bit. This is the old plot we had in the 2014 snow mass practice, which I will introduce later. 2013 snow mass practice. This is the year of physics delivery for different colliders. The vertical axis is the the collision central mass energy of the constituent. We have essentially two lines, right? Lower line is the lepton collider, E plus E minus, for instance. Upper line is the hadron collider, like a proton-proton or proton-antiproton. It's a very busy plot. In fact, I believe even for today's most audience in energy physics wouldn't be able to recognize many of those past colliders. I want to emphasize, it's clear, we try to label various physics discoveries of the past collider. We can see that the energy frontier, whoever can realize the highest beam quality and the highest energy is to new physics discoveries, such as a charm in tau lepton in the early days, gluons, regeneration of neutrinos, top quark 1995, and also W and Z boson, as well as the Higgs boson. And there's a corresponding technology associated with them through the brilliant work of our accelerator colleagues. We can see that clearly. High energy physics drives particle physics discoveries. That's why we often name our field, even though we are really interested in elementary particle physics, call it high energy physics. Okay. But even back in 2014, okay, we have been dreaming for the future. Like we can see those gray lines. We're thinking about the future muon colliders, future very high energy large hadron colliders. Such a dream in our field has been persistently there. It's not out of a sudden that we are interested in future collider. We have been thinking that these will be our primary tool in exploring fundamental physics. Of course, recently, many of you have heard of field, see in the news and in the meetings, those perspective changes more and more. The eager for the community to have future high energy colliders are more and more from both the theory, accelerator, and the experimental community. And there are many interesting physics aspects to examine. And the whole field right now is working actively on the physics cases and also the accompanying technological challenges. So let's just take a look at various physics. This is a very busy plot. You're going to follow every line, but let me give you a brief idea. So this is a line of, this is the physics demonstration line of as a horizontal axis as a function of the central mass energy for future lepton colliders. This is the vertical axis of how much of those leptons I need to collide to deliver a certain kind of physics. And we decide to mark the physics goals in those solid lines, such I want to explore 1 million Higgs, so I can make a precision measurement of the Higgs. I want to make a huge number of Z bosons, as well as maybe I want to explore the effective field theory up to 10 TeV scale or 100 TeV scale. They give you different lines of required energy and the luminosity. Okay. There are many possible basic cases in the solid line, but on the other hand, one should notice, one may not fully get it, but which I'll explain later, but all those dashed lines are different proposed future collider machines, including FCCEE, CEPC, and also muon collider in this line. And there are different running stages of the luminosity and central mass energy. We can see future collider, proposed collider easily surpass the minimal requirement of the various luminosity we want to deliver some basic physics. What are all those dashed lines, those future machines? So there are many proposals ongoing, such as in Japan, we have International Linear Collider trying to collide plus E minus at 250 GeV up to 1 TeV. In China, we have a circular E plus E minus collider, electron-positron collider, with 100 kilometers circumference and trying to collide particles to 40 GeV, later upgradable to 100 TeV PP collision. At CERN, where Large Hadron Collider is, people are trying to proposing the colloquium machine, which is a linear machine that can collide electron-positron at up to 3 TeV central mass energy, or a 100 kilometer circumference machine, the future circular collider, running similarly with Higgs 2.40 GeV running scenario for the Higgs, and also 100 TeV possibility. More recently, there's a generated strong interest from the community into the muon collider concept, where the international community has been working together, and the US has been playing special important roles in putting forward such concept. And in the meantime, we are trying to explore other accelerator technologies to enable affordable future programs. Okay. So having those many future collider programs in mind, we have a great ambition to explore the fundamental physics. Let's take a look at where we are and what's the timeline. Okay. So here's the collection that Energy Frontier made in the last snowmass practice happened last year. Again, we'll explain snowmass later. The currently running machine is called Large Hadron Collider, where we discovered the Higgs boson, where we are doing our upgrades and going to run that until around 2040s. A lot of physics delivery will deliver from such a proton-proton machine. Also, there's a timeline for the various machines I mentioned earlier from Japan, China, and CERN of FCC, for instance, of the E plus E minus version of the hadron-hadron one. Okay, some of you should be shocked to see the horizontal axis, which is a year. Okay, we are 2020s. We're delivering physics up to 2040. This is a running machine, and all those future colliders can even extend to 2090. It's an astonishingly future program. And also in the US, we have hope. We have hope for C-cube colliders or muon colliders. There's optimistic timeline for those machines that maybe we are able to deliver physics in the 2040s. So these are so many different future options. Okay. You may feel up to this point, we are living in paradise. Right? We're shopping the Paradise Bakery for ice creams. It's a really hard choice. However, immediately we should realize, we should realize that we are in Aspen, right? So we have limited money, okay? But even apart from that, actually, for those who are in energy physics or who have known a bit about the energy physics situation, you've already yelled at me. You're so polite, you haven't yelled at me yet. It looks like I'm talking about utopian physics, daydreaming for future colliders. Okay? So you are totally entitled to do so. Let me admit, there are confusions in our field. Okay? The biggest question we ask ourselves is, where are we going? Okay? Many people can throw rotten tomatoes at me by saying the following, any of those following statements, such that, oh, we cannot promise discoveries at future colliders. How can we motivate them? How can we build them? LHC found nothing but the Higgs. LHC will make no new discoveries due to current results. 2-0 series dead. No one can afford a $10 billion projects. Or when those machines are built, we're all dead. Okay, so the rotten tomatoes can be written. We can have those written words on any of the written words on that. Okay, so today my hope for this colloquium is trying to give you some perspective that why those things doesn't bother me and doesn't bother many people in the field, and we're working hard trying to enable our future. Okay, so. First of all, when we are trying to predict the future, we want to learn from a history. It's a good moment this year. Actually, this year is the 40-year anniversary of the W boson discovery. I believe for most of you, you were not intellectually in there yet to witness the double boson discovery. Let's take. I was not. Okay, it was discovered before I was born. So still, I was lucky to be in the talks and try to learn what happened back then. Okay? In 1937, we discovered a neutral current. In 1977, we measured the Weinberg angle from cross-section ratio between neutron and charge currents. And this enables us to predict the W mass. Later on, with higher precision, we predict the W boson, okay, to be at around 80 GeV. Okay? From a different point of view, right, we measure for muon decay the Fermi constant, right, that G Fermi. We measure the Weinberg angle in the electroweak theory. We are able to predict W mass with the following simple equation. Okay? We predict before we discover the state, okay, the mass. Then what happened? We have at CERN, we have superproton synchrotron. We collide particles. We decide to convert SPS into the proton antiproton synchrotron. Okay? We are the technological breakthrough of stochastic cooling. Later on, also got Nobel Prize. The first proton antiproton collision happened at 540 GeV in 81. Collect enough data in 1 year to enable W boson discovery. We discover W boson and make announcement. Okay? And you can see those rings. Those was discovered in this UA1, UA2 experiment, which is using the SPS ring to light the proton and antiproton. The discovery was as simple as this 40 years ago. Okay? It's a function of the electron transverse the electron energy. The W boson, once we produce them, they can decay to electron plus neutrino. We can measure the electrons. From a heavy resonance, there will be typical energy associated with that. So there's an anomalous amount of high energy electrons that we observe in the experiments. Similarly, we can observe muons. In fact, it was in that experiment we also a long debate about what is jet, which later on we understand is the hadronic activities to the QCD. Okay. So, but to make a discovery, we actually use the event without jets, just to make sure we understand what's going on in the underlying physics. Okay. So this physics was established, and we make a W boson discovery. We will learn some lessons from that, which I'll summarize after the next example. Next example of history is 11 years ago, we made the Higgs boson discovery. Last year, we celebrate Higgs at 10. Okay. Again, let me turn back a clock and talk about the historical perspective. 76, we start to talk about Higgs phenomenology, thinking about how we can discover Higgs boson. The first thing the physicists start thinking about how we can discover Higgs, realize we have to apologize. Okay? We have no idea what is the Higgs mass, unlike the W boson that we predicted, we infer. Okay? We're not sure it's coupling to other particles, except for they are very small. So for this reason, the series do not recommend or do not encourage our experimental searches for the Higgs boson. So that's the first attempt we have in the theory community. You can see we are not always selling you stuff. We're trying to actually physically evaluate the situation and make realistic predictions. Very nicely, within 1 year, we established another very important theorem. That's we find that without the Higgs boson, the weak boson scattering will break unitarity at a high central mass energy. Okay? So we know from that either the Higgs mass is below 800 GeV or something else happened, such that we have a so-called no-lose theorem. That if we are able to probe weak boson scattering at high central mass, we ought to discover either Higgs boson or something else that's trying to unitarize the process. And that motivates our very confident proposals and the buildings of various future experiments, such as the LHC, as well as the SSC, which is another interesting story. Of course, we can fast forward the clock, and now all those theorems and all those attempts, this is a plot I like to show, which I believe for those people who already know Higgs is there, they probably haven't seen this plot before. This is a function of Higgs boson mass. Okay. it's a line of one is a line where if the Higgs boson is at this mass, 100 GeV, 200 GeV, or different masses, that's a predicted rate. Okay. So the black dashed line is where the experimental exclusions, combined exclusions from different channels. Okay. So back then, this is roughly 1 year after LHC turned on. Okay. Through lab and the Tevatron, we excluded the Higgs boson below 114 G. Okay. Without LHC, we are only able to exclude the Higgs boson from Tevatron between 160 to 180 G. Okay. The huge spaces are open. We don't know where the Higgs was. And even after we turn on the machine for 1 year, what we only achieve is the big exclusion. We exclude this origin region from the LHC. Okay. So if you think about the time, it has been almost 35 years or 40 years after we proposed the Higgs boson. And we start to discuss the Higgs phenomenology. And yet we haven't found it. We found the exclusion. Powerful machine we built is exclusion. Seems like he either lives in this tiny sliver rate of between 115 GeV to 140 GeV, or somewhere high, some higher energy. Maybe we don't have full access. So that's why I want to say in this plot, we actually clearly see all the historical effort we have made to discover the Higgs. And the discovery of Higgs itself was a huge step forward, because that tells us nature realized actually symmetry breaking in this very elegant and simple form, okay? At least from the bulk part point of view. On the other hand, if you imagine yourself were experimentalist, work so many years, keep on doing exclusions, well, you might give up before the moment of the discovery, right? So that's the challenge part of fundamental particle physics discoveries, that we don't have a guaranteed outcome of this particle you are looking for. And I also feel extremely lucky, because Higgs boson was discovered during the middle of my grad school, which gave me exposure to the series of archive articles where people postulate Higgs boson doesn't exist, did not exist. I still write down consistent theories and write down other UV completions for the standard model particle physics. So in that sense, the discovery itself this form is not guaranteed by our tremendous amount of effort. We made the breakthrough, and they taught us a lot and about nature. So now understood later on, Higgs was discovered in 2012 at the LHC. The Large Hadron Collider is this large ring. 27 kilometers circumference. But I also want to use this ring to remind you, okay, this ring should look familiar with us. It should look familiar to you. Now, this is the proton synchrotron. This is the UA1, UA2 where we discovered W boson, and we have lab, and this is the ring we later upgraded to a proton-proton collider. We finally upgraded energy and luminosity, discovered Higgs boson. Okay. In this sense, we look back in history. What happened in the past is a long lifespan of energy physics program. Okay. Even I didn't even draw the lines before the 1980s, but the lab program where we measure many physics and is still leading many of our understanding of electroweak physics. While lab was running, as an experimentalist, you will be working on the physics analysis and also help with the design and building prototypes and the constructions with the next generation collider, Large Hadron Collider. And while you're working on a Large Hadron Collider physics analysis, as many of our experimentalists does, you also have to work on the design and upgrade and the construction of high energy, high luminosity LHC is another upgrade ongoing project. So from this point of view, it's a continuous upgrade that already going to span more than 40 years, and it's going to span way more than that. In that sense, as energy physics, our dreams are big, the projects are hard and costly, but we have managed to make things happen, and they enabled many new discoveries. From that point of view, one can easily see, for instance, the future circular collider will be in the design, the prototype construction phase, while we are trying to acquire physics from the high Lumi LHC run. That is guaranteed to give us physics output. Or any other future colliders that I mentioned earlier, many different options. Someone can start earlier because they don't need to use the land of the CERN. but it's a multi-decade project, but I think it will be a healthy and continuous physics output. And the process will be fundamentally trained under both physics analysis and the detector design. As well as for the theory community, we will be able to interact and propose new experimental searches and affecting their physics goals for all those future programs. So I hope this clears your confusion about how long we need to wait. In fact, the fact is we're not waiting. We are always busy. There are always interesting physics coming, and it should be a continuous program. Second lesson I want to draw is I think those discoveries spoiled us a bit. We already knew the double boson exists. We know it's mass. Right? We know top quark was there. We made the discovery in 1995. We know Higgs is there. All new physics enters before 800 GeV, according to this no-loop theory. That ultimately leads to many people's claim that if we want to build a future experiment, we have to promise you a future particle discovery. Okay? I would say this is totally false, the wrong logic. The true logic should be research is about the unknown, and we shall not overpromise. Okay? And from now on, I will try to focus on the definite physical outcome, as well as the dream case where it's possible for us to discover some, unpredicted known physics. So before we march into the physics, in fact, this is also 40 plus years of a snow mass practice. Again, many of you may not be aware of what's going on here, but actually, many Aspen participants, you are staying in the snow mass site, where many of this planning happened in history. Okay? So slides from other reviews. Okay? In 1982, there's a snow mass practice, is a gathering of many energy particle physicists trying to sit down, work on the physics, and try to compare and work out feasibilities and prioritize future projects. So 82, people concentrated on the next collider, which is the concept of SSC. Okay? There are subsequent snow mass studies of the design and physics. 88, we were thinking about the energy physics in the 90s, and also research research direction for the coming decades. More recently, there's become a summer study of gathering thousands of physicists trying to study all the possible future particle projects and trying to lay out their physics. This provides input for the prioritization committee and to list a recommendation. And very recently, we had 21 really happened snow mass, and 2013 happened in Minnesota. The last year it happened in Seattle. What people did was really a community study. They studied physics cases for various colliders and trying to work out their uniqueness of different colliders and the cost and the technical challenges to evaluate and access their feasibility. Okay. Of course, it seems like many people actually, since it's the most recent snow mass activity, many of the audience have participated. Thank you all for your contributions. And although it looks like everybody is happily, chatting about physics, but in fact, we work really hard in the background, write many pages of documents to be as input, as important reference physics evaluation for our decision for future. Okay? And again, you should already see why we did this. Because the projects are costly and longer term, it does require community consensus and careful decision making. And that's why we have the snow mass activity. And as of today, first of all, I want to emphasize planning for a long-term future is really hard and requires community inputs and understanding. Now we're looking forward to the P5 report, which is the prioritization reports, and also a National Academy of Science survey report on what to recommend and where the field is going in some of those big projects. So after all those practices, let me come back to what I think where our field are. Okay, to answer where we are going, I think we are doing long-term planning for the exciting physics while we have continuous physics output. And in the meantime, we are also looking into all different possibilities for physics output. Okay. So in the second half of my talk, let me give you highlights of field directions people are actively exploring right now. Okay. And also, I think the status to help with the confusion of our field, I think physics is an evidence-based scientific field. The whole field collectively is working hard to achieve breakthroughs in understanding nature, either from the theory side or from the experimental evidence side. From the theory side, there's many different interesting programs, exciting programs, amplitude program, symmetries, etc. Provides new angles and hopefully leads to new insights where we expect new physics would enter. On the other hand, a large fraction of the community realized that maybe we should collect more evidence from nature about what to come. Instead of guessing supersymmetry has to be there in this particular form. So we realized that the real physics opportunity resides between the theoretically allowed and plausible scenarios and the experimentally accessible ones. You can work on the experimental program, the theory program, and to enlarge the overlap. We can enhance and improve our knowledge of nature. In the School of Physics, so physicists will work in this intersection. I would call ourselves the enablers. We are enabling new insights and new knowledge from nature. Okay. So first of all, the immediate physics is LHC, rocks. We have many interesting LHC talks in this new opportunities for energy physics program. I just want to highlight a few. This is what we measure at the LHC as a function of section for different final states when we discovered Higgs boson. It's already a few years after LHC turned on. And this is how many different processes we have measured of the standard model process today. Various different final states differentially with different number of associated jets. Well, it seems like we're just making measurements. Okay. On the other hand, if you look into them, there's actually a tremendous amount of efforts into the calculations and predictions and checking consistencies with our theoretical prediction. And it's marvelous that we have made so many measurements, and there are many of those predictions and calculations are extremely hard. Sometimes they should break down and have a lot of large, broken apart large logarithm factorizations in question. People make such beautiful measurement and check their consistency with the standard model. And also, after discovering Higgs, we didn't stop. We measured Higgs after 10 years of data collection instead of just barely discovered Higgs. We now measure all its couplings up to 10% level. And in the upcoming future, our projections will give us to sub 5%, a few percent level of all the Higgs couplings. Okay. It's from a bottom-up point of view, okay, a priori, we have our expectation of Higgs coupling to various particles. We know they're small. We know roughly what's their size according to the mass. Okay. We don't know if the Higgs is fully responsible for every particle's mass, right? In that sense, we don't know exactly what's a coupling. In fact, there are many postulations and reasons to believe that Higgs couplings, different particles should differ from the minimal standard model prediction. And also, by having such a wonderful machine, we are actually going to be able to measure various very subtle physics effects, such as interference. A special kind of interference me and my collaborator worked out is even for the Higgs boson, the diphoton decay channel, where we discovered the Higgs. There's a forgotten piece of on-shell interference that will affect our precision prediction. And that has not been captured in the continuous improvement of factorized calculation of a production decay. That could also, such on-shell interference effect could also change our perspectives of discovering new scalars at the Large Hadron Collider. Again, those possibilities are only enabled if we, with our awesome understanding of the Large Hadron Collider, the factorization, and the precision calculation. There's a long list of many programs. We are expecting to have a lot of exciting results from the LHC, with 95% of the data yet to be collected in the upcoming years. But of course, I talk about future collider. I would emphasize future collider physics are focusing on Higgs and standard model measurement, because this is what we can promise. Those measurements will give us a stress test of the standard model predictions. Any deviation will tell us there's something new behind that. It will improve our understanding of precision calculation and the anticipation of new physics. Also, all those future colliders, each of them are discovery machine, where I cannot promise discovery, but I can show you reasonable cases. If such nature prepares such a motivated scenario, we'll be able to find them. So let me give you a few examples. The reason we focus on Higgs physics is because it's deeply connected to many profound puzzles of nature. Because the origin of electric symmetry breaking, why the Higgs potential looks like that? Why do we have spontaneous broken symmetry in such a form? Naturalness, why Higgs mass is so light, and also this origin of masses, origin of flavor. Is this a unique Higgs? And also there's many profound questions. Each of them we can have a lengthy discussion. But it's reasonable to anticipate Higgs is connected to so many profound puzzles of nature. It will be the solution to those profound puzzles will be reflected in certain properties of the Higgs program. Thus, we have the Higgs precision program, and each collider will access the Higgs program in a different way. This is a gluon-gluon fusion into Higgs. We have a triangle diagram. At the LHC, we're producing many Higgs bosons. For this future E plus E minus machine, I can do a D Higgs associated production. Motivates the 240 GeV running scenario, muon collider fusion at 125 GeV, or have a VBF fusion at the 10 TeV muon collider machine. They all have different production modes and reveal us different aspects of physics. In that sense, different future colliders are complementary to it. There's a busy plot. I don't expect you to read into them, but just to give you a sense, different color bars represent different future colliders. The gray bar is what we are having about the LHC, and with different assumptions of the reasonable theoretical assumptions. The lower, the better in this logarithmic scale. The lower means the more precise we're going to measure the Higgs boson properties that allows us to understand more about this microscopic structure. We can see most of the colorful future colliders will improve comparing to the Large Hadron Collider and order of magnitude. And also, there are certain detailed channels where Hadron Collider is better than the future Lepton colliders with different assumptions, etc. This bulk parts to say the community have studied this bread butter physics for Higgs boson, show them some subtle physics effects. We do have a pretty good understanding of what they can achieve for various different future colliders. And also, we can look for something more exotic. For instance, Higgs can decay into exotic final states, into 4 leptons or 4 jets through some intermediate states. Now I can start to postulate, beyond the standard model prediction physics and the model channel physics. We can look for multi-fermion final states, for muons, for taus, for Bs, etc. They can be connected to the class of models where Higgs, I can modify the Higgs potential and try to enhance the electric phase transition. It can help enable us to explain the matter-antimatter symmetry of our universe. Okay. The BS model is not unique, but this class can be robustly probed by this exotic decay program. Furthermore, in connection to our astrophysics and cosmology puzzle of dark matter, okay, I would say weakly interacting massive particle still the most compelling, simple predictive explanation of thermal cold dark matter. Okay. It implies a scale, and the future energy collider will give us access for such a scale. So we work in the so-called the nightmare scenario, which is the hardest to probe scenario of WIMP dark matter. They are in the minimal electric standard model electric multiplets. They can be Dirac fermions or Majorana fermions. The vertical red line is where their mass would be if they want to saturate the full dark matter content of our universe. So if I build a collider, I want to have access to them. If we can cover those vertical red lines, I think I'm touching some very important thermal target. One can do such a search, for instance, at the future muon colliders through a monophoton, monomuon, or VBF process. Also, one can look for the exotic disappearing track signatures, which enable us to do touch the kinematic limit. This example, I also want to emphasize another point that is not only from the direct production and the measurement of those dark matter particles, electric multiplet, we can find them. We can also gain access to them through the precision measurement of electric physics. And also importantly, I say, even if we first made the discovery of WIMP dark matter in future dark matter direct detection experiment, we would want to understand how do they exactly interact with the standard model particle. Okay? Once we know the scale, colliders clearly will provide us definite measures of new particle properties and how their different properties are connected to our cosmological evolution. Many more examples. We can try to use various future collider programs to probe the hidden neutrinos that help us explain the lightness of neutrino mass. Another busy plot. Again, you don't need to read into details, but this is the mass of the neutrino patterner versus the mixing angles with the patterner. They help through the so-called seesaw mechanism or generalized seesaw mechanism explain those tiny mass particles. And the different dashed lines are various future programs there through different search possibilities to probe such kind of physics. Also, interestingly, the Higgs boson has the strongest coupling to the top quark. And in fact, although we motivate the Higgs boson, the existence to unitrize the WW of scattering. In fact, the Higgs boson also unitrizes the WWTT bar scattering. Therefore, now we don't have a precision measurement on their couplings yet. So if the top Higgs coupling to top quark deviates from standard model predictions, we will have unitarity violation processes that the deviation grows with energy. One can use such a possibility to make a precision measurement of the Higgs top Yukawa, which is actually one of the driver to many of the Higgs puzzles. As a hierarchy problem. Okay. Future colliders again will give us access to sub-percent level precisions through various programs. This particular one is through the interference effects. So that's it for the high-energy program. In fact, there are many others I do not have time to highlight, but to give you a holistic picture of our field, I also want to briefly mention that the high-energy physics community is also actively trying to utilize a high-intensity environment, various experiments in preparing for us. We'll see more detailed talk from Stefania Gore next week in the colloquium. Here, I think, let me just explain, give you one quick example of what's going on. Where we all know that the flagship particle physics program in the United States, it's the Fermi, right now, it's a Fermi Lab, a long baseline neutrino experiment. So we are going to smash a large amount of protons into a target to produce neutrinos and let them pass through the Earth, measuring their oscillation properties. It helps us to understand the neutrino, several key parameters of neutrinos. So in the animation, we just scattering particles and let these particles oscillate and try to detect after they transpassing about 800 miles in the Stanford lab. Okay. But for a BSM particle physicist, we want to use them for something else. Such intense neutrino source is also an intense new physics source. For instance, we can postulate the existence. It's a motivated scenario of mini-charged particle. We can postulate the existence of particles with tiny charge, electric charge. We can produce them because of the tiny charge. We don't produce them too much. We need a very intense environment, produce copiously of them and detect them. As such, neutrino facility enables us to do so. We can use a high amount of protons colliding on the target, give us a lot of neutrinos as our mini-charged particles, and we can try to design clever strategies, trying to beat the background and enable a new search for mini-charged particles. Again, this is a function of mass versus how fractional charge they have. The new search enable us to cover new parameter regions that we haven't explored before in this log parameter space. And in fact, there's a lot of activities along this mini-charged particle line, but I don't have time to go through every one of them. Nevertheless, if you realize there's an upcoming DUNE experiment have a 6-order magnitude larger signal rate, and than what we have used deriving this new result a few years ago with a prototype experiment. There are a lot more exciting programs coming, and further than the neutrino detectors. We realized with collaborators that the dark matter direct detection experiments are also automatically an awesome device to look for mini charged particles from the beam. So in fact, working with Sensei collaboration, which is a dark matter direct detection experiment using so-called skipper CCD technology, through repeated measurement, we reduce the noise level down compared to our normal CCD. 3 grams of such a device enable us to derive new constraints in this log parameter space. And the future program of the dark matter direct detection experiments called Oscura will enable us to discover more and more parameter regions. Just a quick glance of how we use the high intensity environment. And also, it's possible to use this high intensity environment to produce and probe other exotic space, such as the hidden scalars or pseudo-scalars. We call it axion-like particles, which can be connected to a strong CP puzzle. We can see that various future high-intensity experiments will conduct such a search and enable new coverage in the axion versus a coupling point. And also in the scalar and the vector case, and also the fermion case that I will skip. In the last 5 minutes I think there's another frontier that we are trying, high energy physicists are trying to make happen. We let 100 flower bloom, which means we talk to people, our colleagues in other fields are trying to realize new physics opportunities in a small scale experiments or tabletop experiments in connection with quantum information science. In fact, in this program so far in the past 2 weeks, we already have 3 talks related to this direction. You can see it's a very active field. I will just give you 1 or 2 quick examples. It's closely related to our traditional high energy collider physics. This device, some of you might recognize, is called superconducting radio frequency cavities. We use them to accelerate the particles. If you recall the animation I showed you earlier, we use them to accelerate the particle to ultra high energy and collide them. Just to maintain such a high accelerated particles without losing them, consistently accelerating them, they are required to have a very high quality factor. And they are required to contain large field strengths. And in fact, we embrace with our condensed matter friends to use the superconducting technology. And that's the standard in our field now. We have the highest quality factor, superconducting radio frequency cavities, which enable us, beyond the accelerator physics and colliders, enable us to think about something else. We are thinking and we proposed, let's do a light shining through wall experiment. The idea is simple. I can power up one of the cavities with a lot of photons, but they would not penetrate the superconducting wall. It's blocking those normal photons. However, if the dark photon exists, those photons will mix with dark photon, and they can generate a hidden dark photon field that is penetrating the wall and making another cavity, which should originally see nothing, see some signals. High quality factor enables many opportunities here. Enable us to have a strong field, enable us to collect a signal for longer. With our proposal a few years ago, we finally arrived at our first Pathfinder result that using the accelerator technology and superconducting technology, we look for dark photons that's the common integrated in many BSM physics, and we probed and constrained such scenario in this log-log parameter space. There's a long way to go, and there are many other possibilities. I'll be happy to talk more in the wine sheath that the field is exploring right now. Beyond that, we can also consider recently more and more activity in this direction. People think the ultralight regime, where you postulate the existence of the dark matter to be in a very light, have very light mass. They behave collectively as a classical field. One can put some ultra-sensitive devices, and the dark matter might exert a force on those devices using various technology of coherent readout, enhancement, squeezing, etc. people can use our AMO friends, this ultra-sensitive device, to look for dark matter. Okay. So just not to overwhelm you with all the different possibilities, I want to go to my conclusion. Okay. I think by now, opportunity does strike at energy physics. I hope for my colloquium, you can see that we have, we're in a very unique time. The field can go in many directions. We have a broad scope of possible probes. And I think we cannot overpromise you, definite discovery in axion or supersymmetry. We are sure whatever we'll learn, we can learn will become groundbreaking. And I hope, and I think our field is having a balanced short and long-term physics. Okay. And I think it's clear to everyone here in Aspen, our best hikes will not be the one labeled with easy parts, right? Those with challenges, confusion, unknowns, and throws. And I think our field is currently enjoying a very memorable hike. A lot of new physics could come. I think, hope everyone feel excited and embrace such an opportunity in this era to come. Yes.
Okay, thank you very much for this nice other questions, please.
Then in one slide, you mentioned about bringing IOC back to US. I mean, what kind of effort we should do to make this happen?
Bring IOC back to US sounds more like a slogan in the slides I still from the snowmass activity. I think currently most promising E+C- proposal in the US is the so-called C-cube, right? Copper collider. And what's required in there, and we see the timeline. We saw the timeline is possible to realize that sooner because this technology is rather mature, just like the ILC. All the key R&Ds has been ILC, all the key R&D has been done. Copper collider needs a little bit demonstration, but afterwards, I think it's possible to do that in the US. And you can view that as a reincarnation of ILC in the US because C-cube do overlap a lot with the technology and also experts in the collider accelerator and vector.
So in terms of the physics mysteries, right? It seems that some of the directions that are many in your slides were about trying to put kind of bounds on certain properties or other parameters of the standard model, like how the Higgs couple to certain quarks or certain particles. And then there were some other things that seem to be more exotic, like Higgs splitting into baby Higgs or maybe charged particles. So could you try and delineate this like a standard model parameters? What are the most pressing questions that are currently on your slides that are beyond standard?
Okay, so very good. The question is profound. Let me try and decompose that. Okay, so there are two layers. One, the first question that you asked is, I can do two things. I can directly look for new physics, axion, dark matter, etc. Or I can just push a standard model precision. Which one is better? Sometimes I go precision, sometimes I'll go direct, trying to direct the probes. Okay. In my opinion, they are both valid and important ways to get new physics. In fact, we all know quantum physics, right? If there are some new state exists, so through quantum loop effect, they will affect the lower energy physics or through integrating out. So precision measurement of standard model physics is actually, in my opinion, also a search for BSM. It's just somewhat indirect in your intuition because we don't produce that directly as an asymptotic state, the new state. However, it has already been proven to be a very powerful method for us to look for new physics. Some of the predictions, the existence of W boson and others actually are through those precision measurement. In fact, we also have a consideration for the Higgs for precision from that perspective. So these are both valid. It depends on what nature have prepared for us. But also importantly, that we have to search both ways because if we don't search them, we may miss them.
I think in that sense, you had slides in the past very fast about what kind of colliders we need to test the thermal hypothesis.
Yeah.
Maybe you can say something about that.
So you're using the dark matter example. Yeah. Yeah. Okay. So this plot is mainly about direct searches. So I want to produce a dark matter state by looking for missing energy, dark matter or missing energy in my collider scenarios. So those are direct search projections. Okay, there's a corresponding electric precision probe in those states. In particular, higher multiplicated representation. Low energy precision test, we can already cover this regime without directly running a collider at 10 TeV. We can run collider at 100 GeV with high luminosity and a very precise measurement. I don't have a plot for the indirect precision constraints on this, but they are complementary to it. So now your second question is about what's the most pressing BSM questions the field have. Actually, one second.
I don't understand it. So this is hadron colliders at this.
This is a muon collider plot. Muon collider plot. Yeah, I skipped all the detail. Yeah. What was your question?
Very important.
Yeah.
What kind of facility we need?
Yeah. So if I have a hadron collider, I would require a different set of studies, different set of channels to access those physics. Of course, for those higher multiplicated whose thermal target is 30 TeV, that will require very high energy hadron collider. Back to your question about what's the most pressing question. Actually, you can one can survey the program participants. Different people have different opinions. That's why I think the field right now is diversifying their pursuit of new physics. Concretely, I think from a more practical point of view, people think questions are very pressing and testable. One is the nature of dark matter. That's why I gave you this example. That you want to understand if dark matter realizes thermal radical abundance through this very elegant mechanism of WIMPs. The other one is actually try to understand the Higgs boson, its potential itself, because Higgs is the only fundamental scalar that was so far to our knowledge, and it plays such an important role through its spontaneous breaking of a particular type of potential that give us electric symmetry breaking and matter their masses. We are positing this, we're guessing it. We actually don't know what the potential looks like. If we're able to measure the Higgs self-couplings of various kind, we are able to have a better picture of why the potential is the potential really what we think, and how it's connected to many other puzzles, such as matter asymmetry or phase transition. Also, there's a company of wave and etc. Just to be fair, there's also mysteries about why we have such a texture of fermion masses, in particular neutrino sector, with a connection to various puzzles I mentioned earlier. It's also quite interesting question that I showed the neutrino pattern searches that can help us.
Any other question? If not, so no, yes. Those two questions.
If you show us your beautiful picture of all the particles that have been discovered.
Yeah, that was great.
Yeah. Almost. So we are any future. Yeah, good. Okay.
So my question is really, there's structure to this. You see these connections between the muons and the quarks. Does this structure give us any indication of to what lower energy we need to go to find the origin of this structure?
What high energy? Yeah.
No, smaller length scale, I meant, yes.
Right. So, well, so there's a long history of us trying to further unify, trying to understand why they are in such a format. Okay? A particular one standing out is the grand unified theory. Okay? So there's a physics scale associated with them, which is very high, but other experts can say more about that. But to me, the unified scale is 10 to 11, 12 GeV, which is very high. Yeah, let's say to 16. Sorry, say to 16. I was thinking about Higgs, but to 16 GeV. However, it's just one beautiful realization. There are many other realizations, such as those forces can be unified in supersymmetry, which actually calls for lighter supersymmetric partners in TeV and slightly above scale. The scale is logarithmic, so I cannot give you a very form. Say it has to be there in 1 TeV. You 10 even higher energy scales. We do, as you said, anyone who stare at such a beautiful structure would want a more reductionism and better symmetry argument and understanding of nature. And it has been driven us through the exploration of nature. It just at this point, we are desperately trying to find a hint of what exact form they are trying to realize, underlying symmetries and this such beautiful structures.
The numbers that you were just quoted are dependent on broad brushstrokes, consideration of the energy scales, second order perturbation theory, and things like that, or if there's something. I mean, presumably the numerology, the sizes of the splittings give you some insight into what might be going on at high energies, independently of the details of the theory. And I was just wondering whether there's a consensus on those scales independently of the details.
To my understanding, there was a consensus in a very simplest form, but later on people realized, and actually many different variations one can have, and in particular, since there's logarithmic dependence and other dependence on the other intermediate scale physics, between grand unification scale, are many variations. So at this point, I'm hesitant to overpromise you that I will find it, in any nearby scale for sure.
I think we have nothing but unification of couples, right? The others were the 10 to 16 GeV.
Yeah. But keep in mind that the grand unification they're talking about is one generation. I think you seem to be more interested in all of these flavors.
Yeah.
And we have no idea of where the origin of the flavors are. There could be weird physics at 100 TeV. There could be physics at the Planck scale. We just don't know anything.
Okay. So in your presentation, you used a lot of potential discovery avenues for potential discovery, and I like that because I'm serious. But it's also true that because sometimes advances come from purely technological developments, like a new device, or so in that direction. What type of things can you imagine? What type of technological developments which might significantly enhance your field?
Significantly enhance the discovery potential. Actually. Let me focus on energy frontier. So how can we probe higher and higher energies, right? One possibility is to in particular, actually, that's the one class is the muon collider I was mentioning. Okay, we never smash muons at high energy, actually maybe even not at low energy, because it's unstable particles. So far, I've been smashing protons, right? Electrons and positrons, those are stable particles. So the ability to cool them down before they decay and accelerate them and smash them together will enable a lot of new discovery channels. Any of the example I show is actually based upon the muon accelerator concept. So another possibility is to having more advanced accelerator technology that make us to have much shorter baseline. For instance, for now we're talking about 100 kilometer or 10, 20, 30 kilometer rings. It costs a lot, and also the magnets. So high magnetic field physics and also high gradient enable acceleration will be extremely helpful in enabling our high energy future explorations, accessing extremely high energy physics. On the other hand, in this light 100 flower blossom direction, actually that's quantum sensing technology, where a significant fraction of our fields also are interested into. that is to work together with sensing community that is motivated by other set of problems, not the fundamental physics problem. To see if there are new physics possibilities can be realized there. And through actually, the dark matter is a beautiful target that have particular properties that drives many of our sensing community friends to think about this class of problem, which has not or may not prominently in their field before. So going to extreme sensitivity with extreme no noise is also a possibility to greatly advance our field. And you can see that all those technological advancement all have connections with our condensed matter friends as well. So I think physics overall is a good community that we should learn from each other and enable new possibilities.
Okay, I think that we should include. So then let's thank Jen again.
Thank you.